Okay, I'll just wait for 2 more minutes. Then we can start our class. Meanwhile, if you guys have any questions, you can shoot out. Yeah. Huh. Uh, oh, okay, okay, okay. Last session is on 20. Huh. Where is that? This is on 27/9, right? Huh. This one, right? Sorry, I didn't share it. Okay. Okay, all right. Yeah. Can you see it now? Which one? Okay, let me know which one. I'll just scroll through, okay? This one? Aha, this one. Hmm. This one? Okay. Right, right, right. I can do that. I can do that. Where is this? Initial was at 0, right? Hmm. You can see my screen, right? Okay. Here is the test, and there are 3 gates, right? And this is the output. Initially, test was at 0, I guess, right? That's what they mentioned. Test was 0, then the output is, right? See, now you can think instead of understanding, like to understand the practical aspect of this, no, you need to understand theoretically what will happen. Let's say ideal zero delay. Okay, for example, you take zero delay, right? If test is 0, then let me take another color. Then this is going to be 1, this is going to be 0, this is going to be 1, this is 0, this is 1. Output of the NAND gate is this is AND operation, and complement of that is NAND operation. 0 and 1 is 0. So 0 complement is going to be 1, right? So this is the previous value, right? And ideally, if I change this to 1, what will happen is if there is no delay across these gate, right? Ideally, this will become 0, this will become 1, this will become 0. And of course, here 1 dot 0 whole complement. Just a minute. Okay. Right. 1 dot 0 whole complement, that is 0 complement. Again, that is going to be 1. This is the theoretical or ideal. Right. So, Bunty, you are clear about this, right? Theoretical aspect. Yeah. Now, practical aspect, you tell me some numbers. How much can I take the delay? Let me take 5 nanoseconds. Right. Now, initial value is, see, whenever you want to do the transient analysis, remember, you need to know what is the initial value and what is the next value, right? So, let's say this is output. Hmm? This output, because initially test was 0, the output is at 1. Very clear, right? This is 1. Now, on the same scale, I will draw the test also. Okay. This is, let's say, t equal to 0, where we are switching the test. So test was 0, then suddenly they switch the test to 1, right? This is what they are saying. Now let's understand this, what will happen. Now this is 0, that means previous values are here 1, 0, 1, correct? Output is at 0, sorry, output is at 1. Now, guys, need to be on time. So test, you make it to 1, right? What will happen? It will take 2 nanoseconds for this to change. It will take 5 nanoseconds for it to change. It will take how many? 4 plus 3 plus 2, 9 nanoseconds to change. And to reflect on the output, it will take 9 plus 5, 14 nanoseconds it will take, right? Somewhere here, right? This much time delay will be there. Sorry, this is test, right? Here is the output, right? Let's say this is 14 nanoseconds. Here only the point of change happens, correct? Now, how much is that, and then we'll calculate, okay? This is the point of change. But till that time, you see, output has to show something, right? So what happens is, this is 1 already. Let's say this is 1. And here still this is 1 only, correct? When it will change? After 4 plus 3 plus 2. It will become 0 after 9 nanoseconds, right? Somewhere here it will become 9 nanoseconds. Like this particular value will become 0, correct? Till that time, both the inputs are 1, 1. So you no need to worry about till 9 nanoseconds. Now between 0 and 9, I am computing what will happen to the output value, right? Between 0 and 9 nanoseconds, this value is 1. Here this is also 1, right? Both the inputs are 1. Like both the inputs are 1, 1 for an AND gate. What will happen? Output will be 0. Does it become immediately? No, it will not become immediately, correct? Even though test has become 1 immediately, output will take how much time? 5 nanoseconds it will take to change to 1 to 0. Are you getting it? So what will happen is, you take till 5 nanoseconds. Remember these timelines, okay? Till 5 nanoseconds, 1 will continue like that. After 5 nanoseconds, output will fall to 0. Then what will happen? The new value will come at 9 nanosecond, right? At 9th nanosecond, the new value of this particular node will come. What is that value? 0, right? Right. So let me redraw this. I don't know what is the exact value here. Let me continue till 5 nanoseconds. Right. After 5 nanoseconds, it will become 0. Then it will be like this. Right. At 9th nanosecond, what is the value came? This is 0. So one side 1, the another side is 0. Then output will take 5 nanoseconds time. So 1.0 whole complement is nothing but 1. That means that output will become 1 after 5 nanoseconds. Means 9 plus 5, 14, correct? At 14th nanosecond, here the output will change to again back to 1. Okay. Since test is always at 1, there is nothing to change. The output has stabilized like this. Okay. So it will become 1, then it has become 0, then again it has become 1. Are you clear, Bunty? Yeah. These kind of problems are frequently asked in GATE these days. Okay. So, okay, let me close this. Guys, today, anyways, we have some. Actually, we are supposed to have combinational circuits part 3, but we are ahead of the timeline. So what I thought is, I will teach you some basics about flip-flops so that everybody will be on page. Believe me, I'm telling you, believe me, after this 50 minutes of class, you will be mastered in the flip-flops. That will be really helpful, for the next sessions. Is that okay for everyone? So that everybody is on the same page? Let me know through your chat. Let me see. Say yes or no, something in the chat box. Okay. Thank you, Ram. Thank you, Anand. All right. Let's start it. Okay. Before I start, mm, hey guys. Okay. All right. Answer this question. For the circuit shown in the figure, if S equal to 1, R equal to 1, then Q is going to be. And this is a, we know this is NOR gate, right? Let me know your answers. Yeah. Any answers, any guesses? You can unmute yourself and then speak if you want. That's what I like, so that I don't need to go to other screen. Hmm? Option A. Okay. Then, how many are going for option A? Let me know in your chat box. Okay. Same. Who else? Any other options? Okay. So that's why I wanted to discuss in detail so that everybody is on the same page, understand clearly, right? So let's see. This is the basic RS latch, right? Right. Today is all about basic, guys. So we will learn the basics and solve the problems, learn the basic and solve the problems like that. And you can ask me whatever the questions that you have, okay? R and S. And let's say this is Q. Let's say this is Q bar. Okay, let's understand this notation, okay? The moment when you enter sequential circuits, we know that the output depends on, when I say output, hmm, this means expected output or next output or future output. People will call it with the different names, everything will be same. And they also represent with the term, with the symbol Qn. Okay, the notation is Qn, right? So I will be using this word most of the time, expected output, because that makes sense. and next output, future output, that's also okay, fine, but expected output is the one, which makes a clarity. So when I say Q, that is nothing but present output, means what is currently available, right? This is the thing that you need to be clear, all right? So now what is a sequential circuit? In the sequential circuit, your expected output depends on inputs, in this case like R and S, and present output. That is important. Okay? Q. Your expected output Qn depends on the inputs and the present output. Right? That's how we can define a sequential circuit. Combinational circuit means your expected output depends on only inputs. Right? So combinational circuits. How to define a combinational circuit? Your expected output depend only, this is important, only on inputs. Correct? So based on this, there was a gate question. You can answer this. Okay, based on just a simple definition. Let me go back. So which of the following statements is true? Sequential circuits are faster than combinational circuits. Combinational circuits are faster than sequential circuits. What do you think? Typically, sequential circuits are faster than combinational circuits. Combinational circuits, yeah, correct. Option B is correct answer. Combination circuits are faster than sequential circuit because, see, how do you form a sequential circuit? What is a sequential circuit? Your hmm, expected output depends on inputs and present output. Means how the present output should be connected with the feedback, right? Means you employ something called as feedback mechanism, right? So this feedback will create a delay. Let's say, for example, I just have something like this. Let's say R, K, and Ks. I have something like this. Right here, the output depends on the delay of one of the gate. Right, that's all. Let's say I will take one gate, for example. Right, your Q is decided by just one gate, and the delay is also decided by this gate. But here, if at all you want to compute Q, what happens is first the data will transfer like this, then it will go like this, okay, then again come back to here, and again stabilize the Q. See how the loop is involved in that. So that's the reason combinational circuits are bit faster compared to sequential circuits. Is that clear? So what we can do right now is, I'll straight away start with the analysis. Guys, please focus 100% wherever you are for the next 20 minutes, because next 20 minutes will decide the entire journey of sequential circuits. If you are attentive enough, that's enough. So, right, we know already expected output is Qn, present output is Q, this is expected output. This is present output, right? So, let's see what happens to expected output. This is also called, what I'm trying to do is a characteristic table. Characteristic table, what happens to Qn? How many combinations of inputs possible? 4 combinations, right? So I can take Oh, sorry, I cleared the stuff or what? Hmm. Sorry, guys. In life also, we should have something like this clear option so that we can forget about all the past grievances, all those things. Hmm. Hmm. Good. How many combinations? 0, 1, 0, 1, 1. And we know what is Qn if I say expected output. Q means present output. Hmm? So present output can be 0 or 1. Anything is possible, right? Right. So like that we have to analyze. So first thing is let's take R equal to 0, S equal to 0. What will happen? You know NOR gate, right? A, B, C. What is C? A plus B whole complement. We know A, B, C if I write 0, 0, 0, 1, 1, 0, 1, 1. 0 plus 0 whole complement is 1. 0 plus 1 is 1. I mean 0 or 1 is 1. 1 complement is 0, 0, 0. From these, what did you understand? If one of the input is 1, output will be automatically 0. You don't need to do anything. That's bound to happen. Just check if one of the inputs is 1, the output is going to be 0. Now here R equal to 0, here S equal to 0. None of the inputs are 1, so I have to calculate other things. But this is Q here, this is Q bar here. So what you can do is, you can assume some value. If Q is 0, Q bar will be 1, correct? So let's assume Q equal to 0, what will happen? So this 0 will be applied here. This will be what? 0 plus 0. Output will be 0 plus 0 whole complement, but that is going to be 1. Already there is 1, you also got 1. This 1 now will be applied here. What is this? 0 plus 1 whole complement, that is equal to 0. Means as it is. If there is 0, you got 0, right? In this condition, you assumed 0, you got 0. Let's focus only on one node, okay? Don't focus on two nodes. Only focus on one node. What is happening? Now let's see what will happen with other condition. What is other condition? Now you assume 0, right? Now let's assume 1 here. What will happen? Here I am assuming 1. Here it will be 0, right? Now I am assuming 1. Now let's see what will happen. This one will be applied here, right? And 0, one of the inputs is 1, so obviously output will be 0. Then 0 will be applied here. Then 0 plus 0 whole complement is 1. Means if 0 is there, 0 will repeat. If 1 is there, 1 will repeat. That means your next state is going to be the present state, same state, right? That is what it means, right? There is no change. Means R equal to 0, S equal to 0 does not change the value of Q, right? Same state will repeat. Okay, this much you need to understand. That's all was. Anything in the sequential circuit is all about this. Mark my words. Now, what is the next condition? R equal to 0, S equal to 1. What will happen? Because one of the inputs to this NAND gate 2, this is NAND gate 1, okay, is 1, obviously the output will be always 0 according to this law, right? NOR gate laws. This 0 will be, no matter whatever it is, no matter whatever is the previous value, whether it is 0 or 1, output will be like Q bar will be at this node, it will be 0. Then 0 will be supplied here. Now 0 plus 0 whole complement. What is this? 1. That's it. No matter whatever is the value of q bar, your output will be at the q bar is 0. That 0 will be supplied to this gate 1. Then the output will be turned to 1. Okay, there is nothing to change in that, right? This is 1. What is this called as? Set condition. Right? That's why it is also called as a RS is what? Set reset latch. Okay, where S stands for set, R stands for reset. Hmm? Hmm. Now what is this condition? R equal to 1, S equal to 0. Because R equal to 1, output of the gate 1 is 0. No matter whatever is the value of Q, doesn't matter. Output will be stabilized to 0. That 0 will be here, and this output of the second gate will be 0 plus 0 whole complement, that is going to be 1. Okay, so this is going to be 0. This is also called as reset condition, right? So far so good. This is the big, this is the thing. The main guy has entered the movie. Right. Now next condition. R equal to 1, S equal to 1. Any guesses, boys? Boys or girls, whoever. What will happen to Qn? Qn is what? You are talking about next state of Q only, right? That you keep in mind. We are only focusing on this node. Yes, correct. Because one of the inputs is 1, this is 0. Because one of the input is 1, this is 0. So the output is 0. So what is answer to this? For the circuit shown in the figure, if S equal to 1, R equal to 1, what is answer? Option C is the right answer. That's all. Anybody disagree or anybody has something to say? How? Forget about the terminology, okay? I say, guys, focus on this discussion very, very importantly, okay? Don't skip anything. Let's say, technically you tell me, logically, you tell me, let's say these two nodes are like this, okay? Forget about Q and Q bar, I didn't write. I wrote some A, I wrote some B, or you can write monkey, donkey, also fine, no problem, output side. Now, logically tell me, if I write R equal to 1, S equal to 1, is something wrong with this? Hmm. Hey, I got it. I got it. I got what you're saying. See, the point is Q and Q bar are the labels that you are giving there, correct? Instead of A and B. Okay. So, what I'm trying to say is, yes, I'll come to the concern that people are expressing, right? That concern I'll see now. So, let's say, for example, this is also correct. Hmm? Now, the issue is this. This is not an issue. R equal to 1, S equal to 1 is not an issue at all. Okay. But the issue is, now for R equal to 1, S equal to 1, output has become 0 and 0, correct? Now suddenly someone want to change the value of R and S at the input side, okay? They changed at the input side, right? What will happen to the output Q? So what might happen is, for example, this 0 will be applied at the input of the second, right? Okay, follow my laser pointer. this 0 will be applied at the input of this gate. This 0 will be applied at the input of this gate. Now the issue is this 0, 0. Can anybody tell me which output will become 1? Because for 0, 0, the NOR gate output is 1, right? Correct? So which output will be 1? Whether the first gate output will be 1 or second gate output will be 1. Do you think it is possible? Both the gates output can be 1? It's okay. I really love the conversation that you are bringing up, because that is the dilemma of many students. Okay, it's okay. I understand. See, this is the concern. The problem is here, right? So, which gate which output should become 1 is not decided by R and S, but that is decided by the circuit elements. Suppose if the first gate is faster, then this gate output will become 1, then that 1 will be supplied here, then this will make sure that this will become 0. Otherwise, if the second gate output is, our second gate is faster in terms of propagation delay and all, then the output of second gate will become 1, and that will drive the output of the first gate to be 0. Did you guys understand what I'm exactly saying? Say yes or no in your chat box. I want to be really clearly sure about this. Otherwise, there is no point. So the outputs, the value of the output is not decided by R and S, but it is decided by the circuit elements. Are we all in the same page? Okay. Is that okay? Is that okay? Now I'm writing that point here. Okay. You have R equal to 1, S equal to 1 condition, which has driven Q equal to 0, Q bar equal to 0. Then if I made R equal to 0, S equal to 0 immediately, then the Q and Q bar is decided by the circuit elements, not R and S. And these circuit element things, for example, propagation delay and all those things, will vary from one family to another family, will vary from one temperature to another temperature, will vary from, at the beginning after 10 years or after 5 years. Means, what are we trying to do? You made this circuit become unpredictable. This is what we are doing. Yes or no? The moment you say something depends on the circuit elements, and that circuit elements functionality is a function of various conditions, you are indirectly saying that your output is not going to be predictable. It's unpredictable system. Tell me, you guys want to design an unpredictable system or a predictable system? Predictable system, right? That's why what they say is R equal to 1, S equal to 1 is not a problem. But immediately after that, if you make R equal to 0 and S equal to 0, you are tend to push the system towards unpredictable zone, which is not recommended as a systems engineer. Anybody should not do that. Reliable system cannot be done like that. Right? If it is made in China or something like that, I don't know. Okay, but reliable system cannot be done like that. Are you getting it? So what we say is generally we avoid this condition. Okay, where is this condition? we say we avoid this. Why are we avoiding it? See, the onset of unpredictability starting because of you are giving r equal to 1 and s equal to 1. So why to do that? You don't even give that condition. Your system will be stable. Okay. Give me a thumbs up if you guys understood this concept clearly. Yes. Only Ram understood. Remaining people didn't understand this concept. Okay, someone else also said that. Okay, fine. So that's the concept, right? Now, this is the only concept I want you to focus and okay, this is the only concept I kind of want you to understand. Once you have understood, you almost have understood everything else because everything else is a small thing, right? This is the main concept that you need to understand, right? Hmm. Now, this is the analysis that we need to do. So first thing is this is the characteristic table, right? This is called characteristic table. That's all. Analysis is over. Now we have to look at different, we have to look at the same analysis in different views. Okay, this is characteristic table. Hmm? Now there is something called as, we all know and then we all like that, right? Truth table. There is something called as truth table, right? Can anybody tell me what is the difference between characteristic table and truth table? Or are they same? If they are same, we will not be discussing that, right? Obviously, that much we know. Any guesses? Hmm. Okay, you can think like this, okay? Hmm. Yeah, we'll come to the excitation table also. Okay. So understand this. Characteristic table is, you see this, this is the output, right? Hmm? According to us, Qn is the output, right? That is the expected state, right? This is output. Hmm? What are the inputs? R, S, and also Q, right? These are the inputs. Now you see, your output depends on the inputs, right? Because Qn is a function of R and R, S, and Q, right? But here Qn is not mentioned in terms of logical value. Qn is in the form of some Boolean expression or some variable something. Okay, those kind of tables are called as characteristic table. Truth table means which gives logical relationship. Oh, what is this? I am very bad at spelling. Yeah. I should learn this. Logical relationships between hmm, logical relationship. Okay, sorry. Logical relationship between inputs and output means that table only should contain zeros and one. That's all, nothing else. Hmm? That's one way of my understanding of truth table and characteristic table, right? Next, inputs are R, S, Q. How many combinations are possible? 8 combinations. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, double 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. This we are avoiding because where R equal to 1, S equal to 1, right? That is there. Now we know if R equal to 0, S equal to 0, how many conditions here? This is the two conditions, like R equal to 0, S equal to 0. Your next out expected state is same as the present state, right? So whatever is Q will be reflected. If it is 0, you will get 0. If it is 1, you will get 1. Then r equal to 1, 0, s equal to 1. Where is that? Here. R equal to 0, s equal to 1. No matter whatever is the value, your next state or the expected state is going to be 1. Then r equal to 1, s equal to 1. What will happen? These two. If r equal to 1, that is enough. Your expected state is going to be 0. Because reset condition, right? Set condition and reset condition, right? And this is not applicable. Okay, you should not apply that. So for every flip-flop, what is important is characteristic table. There are questions, hell lot of questions based on this. Okay, either the questions is on characteristic table or truth table. Okay, now there is something called as, after this truth table, we have something called as characteristic equation. What is this? This equation is nothing but the relationship between inputs and outputs and inputs, right? Now, just a Boolean expression that you need to find between output and input. Okay, we know the output is Qn, right? Here in this condition, it is Qn. Then R, S, Q. I'm trying to find a simplified expression for Qn in terms of R, S, Q. So now let's see. Qn is 1 when 0, 0, 1 combination. Where is 0, 0, 1? Here. 0, 0, 1 is here. Then again one more. 0, 1, 0. Where is the 0, 1, 0? 0, 1, 0. Here, right? Next, 0, 1, 1. 0, 1, 1. Here. Then this is 0, 0, 0 is 0. 1, 0, 0 is 0. 1, 0, 1 is also 0. What happened to remaining two boxes? Any idea what to do? That's it. Very good. Don't care. So this don't care, you can treat them as 0, you can treat them as 1, depending on how much simplification you want to do it. You can treat them as 0 or you can treat them as 1, depending on that. Now tell me, can I treat them as zeros or treat them as ones in this scenario? Because scenario will change from for don't care. Because don't care, sometimes don't care 0. Okay, don't care sometimes, don't care 1. That's a bloody joke. You guys will understand tomorrow. Okay, tell me, in this scenario, what should I consider don't care as? 1 or 0? Right? You can do it in any way. Okay. So let me consider 1. Right? Then I can group these 4. What is this group corresponding to? This to R is changing, so leave it. Q is changing, leave it. So S. Then this pair. What is this? R is 0 and Q is 0. Okay. So Qn is S plus R bar Q. That is the Qn. This is characteristic equation. Then somebody was saying, no, excitation table, something. See, they're very simple. Okay, it's the same concept, right? You have characteristic table. What is characteristic table? Gives relation between outputs and inputs, right? Now, what is excitation table is, you have the name excitation table, right? Okay. You know the present state and you would want to go to the next state. What should be the input values? Okay, let's say I am at 0. I want to be at 0. What should I apply? What should be the value of R and S? If I am at 0, present state, I need to go to the next state as 1. What should I apply? R and S as. Present state is 1. My next state I want as 0. What should be the input values? 1, 1. What should be the input values? That's all. If I want to move from 0 to 0, like it's a simple thing, okay? Can be represented as state diagram. Okay, this is also called a state diagram. Same concept. Okay, so let me write neatly. I am at 0, right? I want to move to 1. What should be R? What should be S? From 1 to 0, I want to come back. What should be the R? What should be the S? 0 to 0, what should be the R? What should be the S? 1 to 1, what should be the R? That's it. Both are same nonsense only on different angles. That's all. So now tell me, anybody want to attempt? Very easy actually. I want to go from 0 to 0. What should be the R and S? Now you check where all the conditions where you are having R0, 0 to 0. This is one condition where we are moving from 0 to 0. Where is another condition here? You see this scenario? In these two scenarios, you are moving from 0 to 0. Now check the corresponding inputs. Here R is, in these two cases, S is definitely 0. In these two cases, S is definitely 0. And R can be 0 or R can be 1. Okay, I am just using my laser pointer and explaining. These are the two scenarios where we are moving from 0 to 0, 0 to 0. In those two scenarios, S must be definitely 0. R can be 0 or 1. Means R can be anything. That means don't care about R. That's all. R can be anything means R can be don't care. First, let me write this excitation table. Then we will come back to the state diagram. Okay, and you guys can try it. Okay. Because I'm not going to repeat this again. I'm telling you. Okay, I will ask you to refer to this video. That's all. That's why today entire session is on only understanding this concept. Right? Any questions? I don't think so. Okay, 0 to 1. Next, what is the scenario? You have to move from 0 to 1. 0 to 1, only one condition. That means R equal to 0, S equal to 1. R equal to 0, S equal to 1. Similarly, 1 to 0. Where is 1 to 0? Find out 1 to 0 here. Here, the last one. For 1 to 0, only one condition exists on one scenario. R equal to 1, S equal to 0. That's a reset condition. You know, no? Right? R is 1, S equal to 1 to 1. 1 to 1, here. 1 to 1, this is one condition. Where is 1 to 1? Here, one more condition. You see? 1 to 1. In these two cases, R is 0, S is don't care. S is don't care. That's it. Done. You no need to remember anything was in digital electronics. Okay. That's why I like digital electronics, because you no need to remember anything. Just start solving it. The entire thing you can do in 5 minutes, so that you no need to remember anything, and then you can just solve it. And you write the values. So 0 to 0. R is don't care, S is 0, 0 to 1, 0 to 1, R is 0, S is 1, 1 to 0, R equal to 1, S equal to 0, 1 to 1, R is 0, S is don't care. Okay, the floor is open for any questions. You have any questions? Did I made understanding of digital electronics easy? Sequential circuits? If you feel yes, you can type yes in the chat box. Otherwise, it's okay, fine. Hmm. Okay, any questions? 2 minutes. I'll wait for 2 minutes. If you have any questions. Okay. Then there is a concept called as gated RS latch. Okay. People sometimes they call it as a level sensitive flip flop. Level sensitive flip flop. Hmm. So here the issue with this guy is right. Q and Q bar, right? When you apply R and S, right? Some values, whatever it is, like when you apply the values, Q and Q bar changes at different times. Okay, it's asynchronous in nature. For one combination, they'll change very fast. For one combination, it will not change at all. It will take long time. So too much thing. So there is no synchronicity, right? So to bring the synchronous thing, what they do is you have a basic RS latch as it is. Right? Q bar. Instead of connecting R and S directly, what I will do is I will put a gate. And gate. This is S. This is R. And this is controlled by a clock. Okay, T clock. Means you have to maintain uniformity across all combinations of R and S. Correct? So you take a clock. So what is this clock does is, okay, like a watchdog. Okay, it will have zeros and ones in it. 1 0 1 0 1 0, right? Whenever T clock becomes 1, these inputs will be supplied to this. Correct? If T clock equal to 1, then R and S will be applied. So I can use the directly characteristic equation. Qn is R S plus R bar Q. No? What is it? What is this actually? S plus R bar Q. Then Qn will be decided by S plus R bar Q. What will happen if clock equal to 0? Your Qn, what will happen if this is 0? This is 0, this is 0. We know, see, this is a actual RS latch, right? 0 0. Why? It's the same thing, right? We know already. If 0 0 means what? Same state will repeat. So you are not changing the state at all, right? This is the characteristic table for this guy, right? If T clock is 1, then Qn is decided by S or Q. If T clock is 0, then there is no change at all, right? So you will give sufficient time for the clock equal to 1 to stay there as 1, so that output will be processed before making clock equal to 0, right? So in this way, we can make kind of synchronous, synchronicity between the outputs and the input, S and R and Q, right? But still, next condition is you are not using all the four combinations as the way they are, right? You are still, you cannot apply r equal to 1, s equal to 1, right? So that is eliminated in the next flip-flop, right? I think I will discuss that JK flip-flop. You do all this, uh, you know, the what is the first thing? Characteristic table, then go to truth table, then characteristic equation, then excitation table and the state diagram, all those things, right? So what is the flip-flop that we have right now? S flip-flop, level sensitive. This is T clock, R, this is S. This is same. This is the routine structure. What I'm saying is this structure is same, right? Fundamentally, this is not changing. This is Q, this is Q bar. What is the issue? You cannot apply R equal to 1, S equal to 0. So for that, what is done is just to tweak it a bit. You take the outputs from here and give it here. You take the output from here and give it here. Like now this has 3 inputs, right? Let me write it so that there is no confusion. There are 3 inputs. I'm not shorting S and Q bar, okay? They are different. This is R, this is S, okay? This is also called as J, this is also called as K. This will become J, K, flip, flop. Now I will discuss about characteristic table. I will not discuss about characteristic equation, truth table and all. So J, K, Q, N. Correct? Now internally you look at it. What is this? This is nothing but a R. This is nothing but a S. This we know already. Let's analyze this. What will happen? Let's assume that clock equal to 1 all the cases, right? Now if this is 0, this is 0. That's the first condition, right? 0, 0. What is this output of this gate? This is AND gate, na? This is AND. This is AND. Output of this AND gate is 0, 0. R equal to 0, S equal to 0. What is the condition? Just go back. R equal to 0, S equal to 0. What is the condition? Same state will repeat. Same state will repeat. You don't need to think anything else. That's all. Same state will repeat because you know the internal structure already, right? That's all. Next. Next, what do you do? J0, K1, let's do. J0, K1. Correct? For this, the output is 0. Correct? For this, the output is decided by this input, right? Because this is 1, this is 1. This you don't know. Okay. For this, what you should do is you assume some value. Okay. Let's say you take Q equal to 0. Then obviously Q bar will be 1, right? This 0 will be applied back. 0, 1, 1. One of the input of the AND gate is 0. Obviously, the output will be 0. R and S, 0, 0 means same state will repeat. 0 means 0 will be there. Correct? I'm just focusing on this node only, right? So 0 is, I applied 0. If I assume 0, I got a 0. Now let's assume something else. Move this, remove this. Let's say I'll assume 1 here. This will be 0, right? I'm assuming 1. Let me see what I will get. This 1 will be applied here. 1, 1, 1. So this is 1. And we know already one of the inputs of the NOR gate is 1. That means what? Obviously output will be 0. This 0 will be applied here. This is what? 0 plus 0 whole complement. 0 plus 0 whole complement is 1. Right? I don't care about this. I just care about this node. Right? So doesn't matter whatever is the value out there, it is always 0. That is why this is nothing but a k. Now similarly, if you can do 1 0, it will be 1. Okay, I will not do that. Right? What I am interested in is this. Let me clear the stuff. Clear everything. Q bar. This is 1. This is 1. Clock is also 1. Right? This is 1. This is 1. This is 1. This is 1. Now again, the output of the AND gate is decided by the another input, right? We have 3 inputs, correct? So you assume Q equal to 0. I am assuming 0. What will happen? Let's see. Right? This 0 will be applied as a feedback. Obviously, this is 1, right? This 1 will be applied as a feedback. 1, 1, 1. Here it is 1. 0, 1, 1. It is obviously 0. One of the inputs is 1. Correct? Obviously, output will be 0. That 0 will be applied here. 0 plus 0 whole complement is 1. Means I assume 0, I got 1. Means this is present output, this is the next output. I mean, expected output. Right? Similarly, you do 1, you assume you will get 0. So what will happen is, okay, it is just a complement. I don't want to do that. I just want to give it as exercise because we are crossing 6 o'clock. It's already 6:02. So if at all you have any questions in that, right? So for 1-1 combination, your Qn is just a complement of the present state. If you want to complement the present state, which is very, very, very important, okay, for your flip-flops in many places, and this combination, especially this combination, right? Many times we will talk about it, okay, in the counters, shift registers, many places. That's the beauty of that, okay. Your up counter basic will start with the 1-1 combination, okay. There I will not explain all these things again, okay. Just go through that. And for the characteristic table, do the truth table, derive characteristic equation, derive excitation table, derive the state diagram. That's all. Thank you guys. Any questions? If you have any questions, you can ask me. I think we are done for the day. Next class, I think bit of T flip-flop and D flip-flop I'll talk about, and then I'll leave. And then we'll enter into the problems. Okay, a lot of problems are also there. Yeah. We have a lot of problems to solve. I want to know how much basics has gone into your heads. Okay, a lot of problems are there. We'll solve it. We have a lot of time to do. If not, chalo, bye bye, tata. Okay, welcome Ramesh. Bye bye.